All right, so in this video, I'm just going to just reveal how a simple circuit like this turns into a quote unquote complicated second order differential equation here. Now, one thing just to note is that even though this is just one circuit, the idea here isn't just that, oh, it applies to just this one singular circuit. We'll eventually do some examples where we're taking the concepts of having multiple energy sources in a circuit and how second differential equation kind of comes out of that. And we'll go ahead and kind of layer that throughout the as we go through different problems here. So first off, just to show like how a simple circuit without a source, how a second differential equation comes out of here. First off, we have just three components in series here. And one thing that we want to look at when we're observing the currents here really is we want to use Kirchhoff's voltage law to figure out what's going on here. Now we're looking at the currents specifically because the currents are the things that will eventually get a second order differential equation based on the current. And as we go through that, we will begin to see kind of how this is all put together here. So beginning with Kirchhoff's voltage law, in series, we have voltage drops across each of the components here. So we go ahead and begin with this. So the drop across the resistor, inductor, and capacitor here. So we're going to go ahead and take each of the terms, and we're given definitions of each of these voltages. So either Ohm's law or just in our capacitor inductor videos, we are essentially just using what is the definition of the voltage drop, or what's the voltage drop across the inductor. Well, we're given this equation, capacitor, etc., and then we're given Ohm's law too. All right, so once we have that, we're going to actually expand out the capacitor equation. We're going to use this version instead, so 1 over C with the integral from 0 to t I dt. So once we have that, we're just going to go ahead and get rid of the negative signs here. So then you end up with the positive values onto just the left side of the equation here. So it's the same equation, just getting rid of the negatives. And then second, next, we're going to take the derivative of the entire equation here. So you can go ahead and pause the video to see how the derivative is applied. But essentially just putting ddt for every single term. Now, what's going to happen is that this term is going to be the second order, the 1 to the second power. So we're going to actually move this over to this side. And we're going to get rid of the L's here. So we're going to move the L's so that you have 1 over L given to you there. All right, so once you have all those put together, you end up with this equation that's squared in the yellow highlighter here. And really, that's kind of the second order differential equation here. So really what this represents is the behavior of the current when it's modeled through a circuit with these two particular energy storing units or energy storing components. So in the next video, we're going to go ahead and look to see, well, how do we go ahead and actually solve for this type of equation?